Hello and welcome. My name is Arthur Drichel and I'm happy to present you our joint work on DGA detection, which we elaborated in the context of ZAPAN. To get started, let's first take a look at traditional botnet communication. Here, bots have usually two simple approaches to contact their command and control server. They either use fixed IP addresses or fixed domain names. But from the perspective of the botnet herder, these approaches have a major drawback as they are easy to block for a defender once these values are known. This is why modern botnets rely on domain generation algorithms. A DGA is a pseudo-random algorithm generating a huge amount of domain names, which are then subsequently queried by the bot to eventually contact the C2 server. Typically, the botnet herder registers only a small subset of the generated domain names, and therefore most of the bot's queries result in non-existing domain responses. These NXTs can be then analyzed in order to detect DGA activities within networks. However, NXTs are not only generated by DGAs, but also by typing errors, misconfigured software, or by the intentional misuse of the DNS. To separate the benign NXTs from DGA-related domains, several binary machine learning classifiers have been proposed in the past which achieve very high accuracies. Going one step further, it is desirable to not only detect DGA-related domains, but also to identify the DGA that generated a specific domain name in order to enable targeted remediation measures. This multiclass classification is far more challenging as there are currently more than 91 DGA families known. In the past, several promising machine learning classifiers have been proposed for these two classification tasks. However, currently these classifiers are hard to compare as there is barely any comparative evaluation of their performance, especially not in a unified setting based on the same real-world data. Selecting the most promising classifier in practice raises additional questions. These include on which traffic to train, in which network and when, just as well as how to deal with the strongly varying amount of training samples per DGA. Moreover, it is unclear which features lead a classifier to a decision, how robust they are against evasion with the help of adversarial examples, and whether the classifiers are real-time capable. Another important property of the classifiers is their generalization capability. Here, it is desirable that the classifiers are time-robust and generalize well to unknown networks. This property enables the outsourcing of classifiers as a service. In this talk, we will briefly go over these aspects and try to answer these questions. First, I present to you our evaluation setup. We use 3 distinct data sources in total. Our source for malicious domains is the open source intelligence feed of DGArchive. DGArchive contains approximately 100 million unique domains, which are generated by 91 different DGA families. We obtain benign NXTs from the central DNS resolver of a university and of a company network. In total, we obtain from these sources 5 one-month recordings of NXTs, which allow for the analysis of the network and time generalization capabilities of the classifiers. For our comparative evaluation, we selected several types of context-less machine learning classifiers. For a feature-based approach, we choose FANCY. FANCY implements a random forest-based classifier for DGA binary classification. We also evaluate different types of deep learning-based classifiers, including recurrent and convolutional neural networks. These classifiers also offer multi-class classification support. We denote the featureless classifiers, which solve the binary classification task, with a leading B, and the multi-class classifiers with a leading M. As a contribution of our work in ZAPAN, we propose 2 novel classifiers for both classification tasks, based on residual neural networks. Let's start with the class imbalance problem. The performance of machine learning classifiers heavily depends on the used training data. Considering the fact that the sample distribution per DGA family is heavily imbalanced, it is not trivial to create adequate training data sets for either of the 2 classification tasks. For example, DGArchive contains the DNS benchmark DGA with overall 5 samples and the viral DGA with over 22 million samples. Hence, it is not obvious how many samples per DGA should be included into the training sets. In particular, it is unclear whether the inclusion of underrepresented DGAs into the training process is beneficial or harmful for the overall performance of a classifier. On the one hand, the classifiers could learn to correctly detect or attribute samples of the underrepresented DGAs, but on the other hand, the overall classification performance could degrade. Since there are usually only small amounts of samples known for recently discovered DGAs, the question of whether the inclusion of such samples in the training set enables the detection of these newly discovered DGAs is of great practical relevance. For our evaluation, we divided the 91 DGAs into 2 groups. The well-represented group consists of 46 DGAs for which more than 10,000 samples are available, The weakly represented group contains 45 DGAs, for which less than 10,000 samples are known. Here you can see the overview of our binary experiment. We created 4 different types of sets. Let's begin with the imbalanced sets. The imbalanced training sets contain for every DGA of the well-represented group 10,000 samples, and 80% of the samples of the DGAs of the weakly represented group. The remaining 20% of the samples are included in the imbalanced test sets. The balanced training sets contain only samples of DGAs of the well-represented group. Here we target the same amount of samples as included in the imbalanced training sets, in order to guarantee that if a classifier is trained on one of the 2 set types, approximately the same number of training samples is available for training. Finally, the balanced test sets contain 1,000 samples for every DGA of the well-represented group. We use each training set to train an individual classifier and then evaluate the classifiers on the different testing sets. Here you can see the average recall for the benign as well as for the malicious class for the different classifiers and combinations of training and testing sets. When prediction is performed on the balanced test sets, the individual classifiers achieve approximately the same scores, regardless of the utilized training set. This shows that the included samples of classes for which only a small amount of samples is known has no significant influence on the classifier's detection capability of DGAs which are well represented. When prediction is performed on the imbalanced test sets, the recall for the malicious class is significantly lower for the classifiers which are trained on the balanced training sets, compared to the classifiers which learn classification based on the imbalanced training sets. The recall for the benign class does not differ much between any of the classifiers. These results show that samples of underrepresented DGAs should be included in the training set for DGA binary classification. Now we come to the MultiClass experiment. Here we investigate the effect of class imbalance in 2 separate scenarios. In the balance scenario, we created a dataset which contains 10,000 random samples for the DGAs of the well-represented group. Additionally, we include 10,000 random benign samples. We then performed 5 repetitions of a 5-fold cross-validation, where we split the samples of each included class into 80% training and 20% testing samples in every fold. In the table you can see the results for the balance scenario. All classifiers achieve comparable results. To further visualize the classification performance, we provide the confusion matrix of our ResNet-based classifier on the right side. Each block within the figure represents the fraction of samples of the class on the vertical axis, which is labeled as a class on the horizontal axis. A perfect classifier would correspond to an identity matrix of black blocks. The benign class is located in the top left corner, and the DGAs are alphabetically sorted. It can be seen that the benign class can precisely be separated from all other classes. Most DGA families are easily recognizable. Now we compare these results with the imbalance setting. Here we additionally include all samples of the weakly represented group. This time the labels are barely readable, but I will summarize the results. The average F1 score over all 92 classes is generally lower compared to the average F1 score over the 47 classes of the balance scenario. However, the 46 malicious classes used in the balance scenario are detected approximately equally well in the imbalance scenario. The only exception is PIXPA2, since it generates similar domains as its related DGA family PIXPA2S. The biggest outlier is DNS benchmark, whose F1 score depends on the classification of a single sample that is included in the testing set of a fold. For 22 of the 46 additional classes included in the imbalance scenario, the classifier is able to achieve an F1 score of more than 90%, and for 11 classes, even an F1 score of more than 99%. Our proposed classifier is able to achieve an improvement of over 6% in macro F1 score. This means that our classifier is able to correctly classify samples of several classes, which the other classifiers are not able to correctly attribute. Similar to the binary experiment, these results show that the weakly represented DGAs should be included in the training sets of a DGA multiclass classifier. But what are actually the features a deep learning classifier extracts and uses for classification? To answer this question, we strive to explain the predictions of the deep learning approaches by investigating the falsely attributed samples from the MultiClass experiment. To highlight some of the self-learned features, we extract simple regular expressions for each DGA. The table shows an excerpt of these expressions grouped by similarity, including the number of training samples per DGA. For instance, Remnit generates strings of length 8 to 19 using only characters from A to Y and then appends the dot and one of the 4 possible top-level domains. In our experiments, a huge fraction of BEDIP, Deergroup, Gosnam and Hesperbot are falsely labeled as Remnit. Considering that a huge fraction of the domains generated by these DGAs match the same regular expression, this is not surprising that the classification is biased towards the better represented class, in this case towards Remnet. By investigating which specific samples are falsely labeled, we can draw conclusions on the possible features used for classification. For instance, within the samples of BEDIP, which are misclassified as Remnet, there are no samples which contain numbers or the character Z. Consequently, we reckon that the set of characters included within domain names is used as a feature to separate different DGA families. We also reckon that the domain length is used as a feature for classification. The separation based on the length is observable on the samples generated by Feodo, which are classified as black hole, since no samples of length 18 are mislabeled. Lastly, we reckon that a top-level domain is used to separate different DGA families. Investigating the samples generated by Odero, which are labeled as vidro, reveals that no domains which use the .cc or .tv top-level domain are mislabeled. So far, we only identified features potentially learned by the deep learning classifiers, which are also easily recognizable by a human. In the following, we will examine the capability of the classifiers to extract more complex features. To this end, we use implementations of reverse engineered DGAs to generate a dataset which incorporates samples of two DGAs which are not distinguishable via their regular expression. For this, we use the DNS changer DGA and adjusted the decrypt DGA such that the domains it generates match the same regular expression by fixing the length to 10. The table shows the average results for the different classifiers. Fancy and the NYU model fail to separate these two classes and are very close to random guessing. The endgame classifier achieves a slightly higher accuracy, and our ResNet-based classifier outperforms all other approaches with an accuracy of over 69%. The ResNet classifier is thus able to label a huge fraction of samples based on the use-generating algorithm with a probability significantly higher than random guessing. To further address the problem of the lacking explainability of deep learning models, we currently develop a visual analytics system in Zapan which tries to bridge the gap between human understandable features and the non-explainable predictions. Recently, different adversarial DGAs have been published which try to evade the detection of a classifier. Here we assess the robustness of the classifiers against two attacks. The Chabot DGA randomly selects a second-level domain from the Alexa top domain names, replaces two random characters, and appends one of 22 top-level domains in order to generate a domain name. The Deception DGA was iteratively developed and targets Fancy by exploiting its handcrafted features. The upper part of the table visualizes the true positive rates for both DGAs at two different false positive rates when the classifiers are trained on non-existing domain responses. The lower part of the table shows the related work, which used resolving DNS traffic or Alexa top domain names for training. It can be seen that all classifiers are robust when trained on NX traffic. As could be expected, classifiers which are trained on Alexa top domain names are easier to fool since both evasion techniques used Alexa domains for their creation. Classifiers which are trained on resolving DNS traffic are also easier to fool compared to the classifiers which use NX traffic for training, because the domain names of the resolving DNS traffic are naturally more similar to the Alexa top domain names. While training on NXDs does not enhance robustness against adversarial attacks in general, it increases the effort required to generate adversarial domains, as an attacker has to be in possession of an appropriate NX traffic from a sufficiently large network in order to craft such a DGA. Next, we analyze the generalization capability of our ResNet-based binary classifier. To show that the classification can be outsourced as a service, we train the classifier on samples of the company network and let the classifier predict samples of the university network. The results of this experiment are depicted in the table on the right. On the left side, we display a baseline in order to be able to assess the classifier's capability. It can be seen that the false positive rate slightly increases. This could be explained by the fact that the benign samples of the one network miss specific properties of samples of the other network. We also performed this experiment for the other direction and obtained similar results. Since the increase of the false positive rate is rather small, we argue that the classifier generalizes well to different networks. We also performed a time generalization experiment, in which we trained the classifier on samples which had at least a time difference of 1 month to the samples of the testing set. We then repeated this experiment with a larger time difference of 17 months. The main result of this experiment was that the classifier is extremely time robust and frequent retraining is suggested on the discovery of new DGAs and in order to reduce the false positive rate. Lastly, we evaluated the training and classification speed of the classifiers. In the table you can see the training time per classifier and the required classification time per sample for both DGA classification tasks. In order to assess the real-time capability, we measured the average and the maximum peak of the NXTs generated in the company network. When performing simple calculations, it can be seen that all classifiers, including our newly proposed ResNet-based classifiers, are real-time capable. In summary, in the context of our research on DGA detection, we proposed two novel classifiers based on residual neural networks. We showed that our proposed binary classifier is able to extract complex features, is time robust, and generalizes well to different networks and can thus be outsourced as a service. Our multi-class classifier is able to achieve an improvement of over 6% in macro F1 score while requiring 30% less training time compared to the second-best classifier. Moreover, we performed a study on the effect of class imbalances on both DGA classification tasks and demonstrated the high value of a few samples per DGA. Additionally, we investigated several important properties, including the explainability, robustness, and real-time capability. In future work, the effectiveness of sophisticated evasion techniques could be investigated, and it would be interesting to further examine the complex features used by the deep learning classifiers. With that, I would like to thank you for your attention.